Yeah, ready for acceleration.
Oh,
Hey, look at that.
here's one he prepared earlier.
Something I prepared earlier.
Yeah.
So, this is where we just got to, right? And if we're thinking about acceleration, where's the acceleration phase all going to be? At the instant where what we're talking is we're at equilibrium position, we're heading right at maximum speed. Where's acceleration? Opposite to displacement. How much is acceleration at equilibrium position?
Zero.
Max zero, max zero.
At equilibrium. There is no equilibrium.
Zero, right. And so we're going to draw it on at zero, but in the opposite direction to the velocity.
You draw it on at zero.
So there's our acceleration phase over there, and check these out. Like these relationships between these three phasors are fixed. Like the displacement is always 90 degrees behind the velocity one, behind because they're going around that way, right? And the acceleration one is always 90 degrees ahead of the velocity, and these two are always 180 degrees offset. So 90, 90, that's going to be fixed no matter what. And so that's going to be a really useful thing when we come to solve problems. So we know that y is a sin omega t, and we know that v is a omega cos omega t. And we're going to have a think about how much the acceleration is. Check this out. Back over here, circular motion, we know that a is v squared over r, and our v max was a omega. Let's put that in for v. We're going to get a squared omega squared over a, because the radius of the circle is the amplitude. And that just cancels out to leave us with the length of our acceleration phasor is a omega squared. Let's write that on. A omega squared, and once again, let's write that down as a function of time. So like we're thinking, we've got our acceleration phasor, and it starts by pointing off to the left, and after a certain amount of time it's going to rotate around to somewhere else, which might be there. We're going to, just to help us think about what's happening, we're going to put a set of axes on there and call them acceleration axes. And like we know that down here, that's the maximum, that's a omega squared. What we're asking is how much is a? How much is that one there? Should we draw a right angled triangle? Go on. And so the angle that it's turned, theta, is equal to omega t. We're picking up a pattern here that the angle is the speed times the time, the angular velocity times the time. And we've got a right angled triangle. Which side are we trying to find? Opposite. And so we're going to go dan sin theta is O over h. We're trying to find the opposite because that's what the acceleration is. A is O, right? That's confusing. O equals h sin theta. How much is h?
A omega 2.
Yeah, a omega squared, a omega squared. That phasor stays the same length. So that the phasor stays the same length. That's really important. Like the size of acceleration is changing, constantly changing, but we can model it with a phasor of constant length. So a omega squared sin, how much is theta?
WT.
Omega t. And is it just me or is it negative?
Yeah, it might be negative.
So minus a omega squared sin omega t. Some of you will remember we started with this, that v is a omega cos omega t. And some of you will be happy that acceleration is the rate of change of speed, right? dv by dt. So A is dv by dt, which is d squared y by dt squared. Some of you might remember that. It's the double differential of the velocity. And so if we differentiate cos, what do we get?
Negative sign.
Minus sine. And if we differentiate omega t, what do we get?
Omega.
We get an omega, so we're going to have a omega squared sin omega t. Like that. And we're like, damn, it's the same. And so calculus makes our lives easier. So if we're good at doing calculus, we can just differentiate.
Are we allowed to do that in the exam?
If you were deriving, if the exam asks you to derive the equation, and you're confident to differentiate, differentiate. It's not cheating, it's doing maths. Huh? And so then the question that you're asking now is, okay, that's cool, but why do we care? I haven't started this one. I didn't get that far ahead. Sorry. Back at the start, like at the start of time, there was we had acceleration.
That's what you said.
Do you remember that? We had acceleration
Yeah.
is opposite to displacement, and acceleration is proportional to displacement. That's like our fundamental key underlying concept of SHM, of simple harmonic motion. And so when they ask you what's the fundamental underlying concept of simple harmonic motion in the exam, you can say, oh yeah, acceleration is proportional to displacement, and acceleration is in the opposite direction to displacement. And so we're like, okay, displacement. Y, let's get our colour codes right, hang on a second. Y is equal to A sin omega t. And A, acceleration is equal to minus A omega squared sin omega t. And so kind of like compare these two equations here. We're like, well, A sin omega t, there's an awful lot of that down here, isn't there? So let's just rewrite acceleration as, well, what's the important things? We've got a minus sign,
Negative.
that's not up there, we've got an omega squared. But apart from that, it's just y. And so then we're like, aha, that tells us that when we did this equation right back at the start, we said the k was just some number to make things work out. But now, having done all this work and comparing our displacement and our acceleration equations, we can see that that k is actually just omega squared. What's omega?
Angular velocity.
Is it
It's the
V
angular velocity. Angular velocity, or we sometimes more often call it angular frequency in the SHM. Either way, it's in per seconds. But how do we calculate it? Omega change in angle over change in time. Yeah, we can. That's kind of like a devil. No, that's an okay equation. That's an okay equation.
V over R or
Yeah.
2 pi F.
2 pi f or
2 pi 1 over t.
2 pi over t.
Yeah.
So we've got some. Ah, but look, this what's t?
Time period.
The time period, the time it takes for our motion to repeat itself. So you mean we've just managed to write down an equation that's got the period of motion in it? So we're now going to be able to start calculating how much is the period of motion of something swinging back and forth. The A is the acceleration, ms minus 2, and y is displacement in meters, and the minus sign means they are opposite in